All right, you're with me. Um, oh, that's the ladybug. I want this guy. There we go. And we will make me smaller and put me up in the corner. Whoa! Shop now. I can get some more Hager's, some more old guy slacks. Nothing like old guy slacks. Hager slacks. Now, here's something I want you to do. In fact, I'll make myself bigger, and because all we need now is a sheet of paper, and we're going to talk about air, wind currents, and things like that. So I'm going to go ahead and cut off a sheet of paper here. Just another sheet, just another strip of paper. And you probably did this in junior high too. A lot of the good science that you did was in junior high when they were trying to keep your little hands busy. Then all of a sudden you get into high school, and hopefully you went to a high school where they had good stuff going on there. Let me turn off my email so that, because if you're like me, you get 14 a minute, and it gets very annoying when you're trying to do something and people get, hey, that's what emails remind me of when you're trying to do something. Hey, I just walked in the room. Get out of here. All right, so here we go. Now, here's a question. Which has more pressure? Fast moving air or slow moving air? There's the big question. All right, which has more pressure? Fast moving air or slow moving air? Or fast moving water, slow moving water? We treat everything we treat air because it's an atmosphere. We treat air as a fluid, as kind of a bulk fluid. It's just not near as dense as water is all. And so, so which has more pressure? Fast moving air, which can, you've seen leaf blowers, they hit you, bam, hit you with a force. Wow, that seems to have a lot of pressure. Or does slow moving air have more pressure? Huh, or water? Well, here's a little experiment we can do to find out. I hope this works. I'm sure it will. I I have all the confidence in the world. Not anyway. So so go ahead and you don't need scissors. You can just rip this off. All right. So what we're gonna do is we're gonna blow like we're a flute player, or when you have a Coke bottle, a real Coke bottle, and you go and you get that boom boom sound. We're going for the boom boom here. All right. This is how we do the boom boom. Okay. So here we go. Ready? Ready? I'm thinking about other things I want to do with you today. Or we've got one more little thing after this to do. All right, so here we go. I'm going to blow it down here. So if I'm blowing it down here, that must mean like the force is going to curl it up under my chin more likely. That's why I'm trying to get the air to blow it up. Well, uh-uh. It's blowing straight out. It's lifting up. What the heck? It was supposed to curl around this way, but it's lifting up. Interesting. So the fast moving air must have less pressure because all the pressure back here is lifting it up. And this is true. Right? And here's what it looks like. And this is for a jet airplane or things like that. It's kind of how things fly a little bit. We have a really cool Bernoulli machine. I wish I probably should have gotten it and filmed it today, but anyway, I we get a misconception of. I want to make this smaller. Okay, there we are. But I want to keep this going. All right, you've seen me, so I'm going to cut out of the picture. All right, so here we go. I got to make sure that I'm still being recorded. So here's what it looks like. Here's an airplane wing, and this is not all how airplane wings work. All right, they cut through the air, and these particles over here on the top, and you'll see this 100 times, and in science, and these air particles that are going through here, they meet. These two split up and they meet at the same time. So this one had to go faster. However, the pressure, the force, is actually lifting it up here, because pressure is equal to force over area, all right? And so the pressure times the area is equal to the force. And this, but also due to the Bernoulli effect, slow moving air has more pressure than the fast moving air. And it's due to the conservation of energy. Okay, conservation of energy. So the slow moving air has more pressure than the fast moving. So this fast moving air is going fast, has less pressure. So the P on top and P on the bottom, P on top is less than the pressure on the bottom. And since pressure is equal to force divided by area, since the area is the same, the area of both of the bottom of the wing and the top of the wing pretty much the same, okay, then we can cancel out the area. So the force on top is less than the force on the bottom, which is why things move. Now, that may not be a big enough convincing argument for you. Think about this. Think about water, right? When you have a garden hose, right? There's another force in nature. If you're using a garden hose, especially when you were younger, if you're using a garden hose and your little brother or sister comes walking by, what do you do? Absolutely. You spray them. You can't help it. It's just something that you have to do. You must spray them with the water. So when you take that nozzle and you hold it over the top, where do you feel the pressure? Behind your thumb or in front of your thumb? Behind. Because that pressure, that extra pressure of the slow moving water is what's pushing that thing through a smaller opening so that it goes faster, and therefore you can hit your little brother or sister and get them wet. So that's how that works. All right. So there's a small little scientific experiment to do to validate something, and all we needed was a sheet of paper. And plus we had that fun little math trick. All right, we've got one more little project to do, and we'll do that next.